In this video, we're going to take a look at one of our first sort of big techniques of integration that we're going to have just past sort of the basic taking the antiderivative. So what we're going to do is start with a little bit of differentiation just to kind of get our head in the right place to be thinking about what we want to do if we're going to undo the chain rule. So we've got two functions here where we need to take the derivative using the chain rule. So remember with the chain rule, we have a function put into another function. So for example, with f of x, we have x cubed minus 2x plugged into x to the fifth. So when we use the chain rule, we take the derivative of that outside function. So in this case, it's that to the fifth power, then times the derivative of our inside function. And that's it. We've done it. We've taken the derivative. There it is. There's not really any simplification that we need to do at this point. You could distribute the 5 through to the 3x squared plus 2, but it's not going to, or minus 2, but it's not going to do anything for us at this point. So we're not going to do that. So taking a look at g of x, so a reminder with this one that when we write that squared right there by our sine function, that is that sine function being squared. So its derivative would be 2 times sine of x. So again, taking the derivative of that x squared part of it, the squared part on the outside, leaving the inside function alone, and then times the derivative of our inside function. So now that we have these two and we know what their derivatives are, we know what our original or antiderivative was, we can look at these and help us come up with a technique that we can use to get our antiderivative, to take our integral. So we're going to work backwards. So we're going to take this one that we just looked at right here, our first example, and there is that derivative we came up with, and we want to get to the antiderivative. Now, we know what we should get. We know we should get, this function up here. But the question is, how are we going to be able to see that when we're looking at something just given to us like this? So one of the tools that we have at our disposal is to do something called substitution. So what we're going to do is take this sort of slightly more complicated polynomial, the x cubed minus 2x, and we're going to call that u. We're going to label that bit of our function as a different variable. We can totally do this. This is an okay thing to do. It feels like we're breaking some rules here. But what this does is turns our integral into this. Now, this kind of looks even more like a worse mess. We've got the integral of 5 times 3x squared minus 2, and then u to the fourth, and then dx. So we've got x's, we've got u's, we've got all sorts of stuff going on. But if we take a look at this sort of definition of a variable that we made, this is our substitution. If we take the derivative of both sides, so we'll say take the derivative of both sides. Right, so when we do that, on our left-hand side, we get du dx, and on the right-hand side, we get 3x squared minus 2. And something that we can do, which again feels like it's, a little bit of a trick, but it's not. This is allowed. Well, here we're dividing by dx on the left-hand side, so we can multiply both sides by that if we want. And we get du is equal to 3x squared minus 2 dx. So now if we look at these two pieces right here, right, we've got that 3x squared minus 2, that's sitting right there in our integral. And we've got dx, which is sitting right there in our integral. And we're saying that this is going to be equal to du. So those two things that we've underlined there in purple and red, we can replace those in our integral with du because they're equal. Why are they equal? Because we said they were, which is always kind of the fun circular logic with this. It's like we've made this true, but all we've really done is done a substitution so that we can see that, oh, what we really had was something raised to a power. We used the power rule on that, which is what we did sort of that first part of our chain rule, and that gave us our derivative. And now once we have this simpler integral, we can use that power rule of integrals to get back to where we started. We can add 1 back to the exponent, divide both, also divide by that 1 plus our exponent, And so we get u to the fifth plus c. And now at this point, we've kind of outgrown the need to have this written as u. We did that again, so it gave us a simpler integral. And u is equal to x cubed minus 2x, again, because we said it was. And we get back to that original function. Now remember, with these definite indefinite integrals, we don't end up exactly with the function that we started with because we might have had a constant there. We're not sure. But we basically ended up right back where we started. So that's really the big key about this u substitution. All we're doing is we're doing the substitution so that we can make ourselves have an integral that's easier for us to see what rule we need to use. And so we're going to do the same thing here. Now, because we know kind of what we started with, that we started with that sine function, our inside function was sine of x, that's what I'm going to make my u. So u is going to be equal to sine of x. And always when we are sitting here at this point where we've got u is equal to, what we've decided u is going to be, we'll talk a lot about that in class, what that needs to be, we're going to take the derivative of both sides of this. We're going to do this every time. So derivative of sine of x is cosine. And every time we're going to take and multiply both sides by this dx. So if you start to, get annoyed with having to do that sort of second step there, you can always go straight from, here's my u, and then here's what du is equal to. So we can replace this kind of piece by piece to kind of help us out. So we said u is going to be sine of x. So that, at least that first part of it gives us u, 2 times u cosine of x dx, and then cosine of x dx right there, which is in our integral, that's equal to du. So we can replace our cosine of x dx with du. So again, what we've done is turned this into an integral that we know how to find. This is u to the 1 power. So we're going to use that power rule again. So we're going to get 2u squared over 2 plus c. And then now substituting back, because again, we only do this substitution so we can kind of get that integral taken and realize what it was that we started with. So u is sine of x, so we can put sine of x back in there. Oh, and the 2's cancel, so we get sine squared of x plus c. And that's what we started with. Now again, it's got this, maybe it has a constant term, but we don't know. Now this one's actually kind of really interesting because we could have absolutely, and every once in a while when I do this one, a smart student says, hey, couldn't you make u cosine of x? We absolutely could have done that. If we did that, here's what we would have ended up with. We end up with something a little bit trickier because we end up with negative sine of x dx. And after we do sort of that first part of the substitution, and we get the integral of 2 sine of x times u dx. Inside of our integral, we've got a sine of x and we've got a dx. We've got those two things, but what we don't have, because we don't have this negative, we don't have a negative 1. Well, you know what we can do? We can multiply both sides by negative 1 so that we get negative 1 times du is equal to sine of x dx. So we are going to replace the sine of x and the dx that we do have in our integral with a du and a negative 1. So the thing to remember about substitution, and this is what we'll spend a lot of time doing in class, is that constants can be moved around. So we get 2 times negative 1 times u du. So again, what we've done is turned this into an integral that we know how to take. And we get something very similar to what we did up above, but this time we have negative 2 u squared over 2 plus c. And at this point we can substitute back, but we have to remember we had cosine of x, that was our u. So we're going to get negative cosine squared of x plus c. And we go, At this point, it feels like, wait, those are two different functions. Well, are they though? So let's take a quick look at these two functions graphed. Notice they're the exact same function. They just differ by a constant. If you take negative cosine of x and you add 1 to it, then they are the same function. So this is that idea that we get a family of functions, and these are the exact same functions. They just look a little different, and that's something that happens sometimes with our sines and our cosines, and both of these answers would be right. So again, what we're doing here, here's our theorem from our textbook, is that we have a derivative that we found from the chain rule, and we're trying to undo that. So we're kind of trying to figure out what was it that was that inside function, and we're going to say that u is going to be equal to that inside function. And what we're hoping to do is basically get our integral down to what rule was it that we used on that outside function that can help us get our integral, and then we can substitute back and get back to where we started.